Okay. All right.
Maybe I want to go back.
I was telling them wait a few minutes. I think we're ready to go, but we'll give it just a few more minutes. I know myself, I was running just a little bit behind packing up and everything. But during this time, if everyone, well, first of all, welcome, and the stalwarts that are here for the rest of the last day of the conference, thank you very much. I've been coming many years to the conference, and I get more than full value, and Jean's an awesome host for it. If we could take a moment and silence our cell phones. I know myself, I'm going to double check and make sure. Yeah, I'm looking good here. I don't want to be a hypocrite. And if there are questions, we are holding them to the end, but I'll ask Jean if we're good on time. Sometimes an immediate question doesn't really hurt. I'm going to be popping up and down. We have 4 speakers and presenters today. And the first speaker will be Joelle Simonpietri. See, did I get it good enough? I'm going to put a little spin on the end. We had fortunate to have share a dinner with her last night and had a lot of fun jokes. But without much ado, her title is in the change. You want to cue up her slides? Thank you. And there we go. Okay. Joelle, I'll turn it over to you.
Hi, good morning. I'm Joelle Simonpietri, which is difficult to spell or say. So to email me, it's just joelle@alohacarbon.com. That's probably the easiest way to reach me. Okay, so Jean asked me to talk about technical stuff. So we got some technical stuff, mostly about a deep dive on the feedstock that my company is focused on, which is construction and demolition debris. And then also sort of listening to the proceedings yesterday, there was some folks who were asking for more information on projects. So I added some information on the projects that we're developing as well. And disclaimer at the bottom, at this point in time, all of our project development work as well as technical work is actually funded by federal grants, mostly from the Department of Energy. Okay, so a little bit about my company. We are not based in California. We're not even based in the continental United States. So a lot of what you're going to see is sort of based on this view of trying to do problem solving for island communities where there's not a whole lot of options. There is a fair amount of industry, contrary to popular belief, and I don't live in a grass shack. Okay, so we've got a small team. We've got 10 people, not everybody shown here, mostly engineers, and myself, I am not, but I feel like I have become one. Okay, so some of the problems that we are focused on tackling for the city and county of Honolulu, which is where we're based, is number one, there is one construction and demolition debris landfill for the entire state of Hawaii. It has 3 years of life left. It's also located in a neighborhood that has the largest population of Native Hawaiians in the state and is also the lowest income census tract. So there's a lot of community support for doing anything that involves landfill diversion. We're also tackling some other issues. Energy in Hawaii is quite expensive. Just the cost to land liquefied natural gas in Hawaii is $30 an MMBTU. So we can actually come in and compete with fossil fuels with renewable natural gas produced at our projects. Okay, so here's a little bit about construction and demolition debris. So construction and demolition debris is what my company focuses on, again, because we started with solving local problems, and construction and demolition debris disposal is one of them. However, it's actually not that different nationwide. There are some unique regional differences. For example, there's a lot more treated lumber in the waste stream in Honolulu because of the termite issues, the same thing in the Gulf Coast, but building materials are building materials. They're either made in the Pacific Northwest or made in China, and there's actually a lot of uniformity. So This map here is of actual registered construction and demolition debris recycling MRFs. From a project development perspective, we usually partner with a company that already has a C&D, transportation and hauling and materials recycling facility infrastructure. In Honolulu, there is none, so we're more vertically integrated there and building our own MRF. Okay, so a little bit about treated lumber. For those of you who know anything about treated lumber, you know that chromated copper arsenate, which is the green treated stuff, is supposedly no longer sold anywhere in the United States. That's basically a voluntary, self-imposed kind of ban by the wood products and lumber treatment industry. However, it's been replaced by borate-treated lumber, and in order to get the same amount of insect damage prevention, you need to really sock it with a whole lot of borate-treated lumber. So, and I'm sorry to enthusiasts here, if you are talking about putting construction and demolition debris wood into your thermochemical process and you don't have a plan for the heavy metals, you're fooling yourself. So, and in Hawaii, 100% of the dimensional lumber is treated. You cannot get it without lumber treatment unless it's a special order. If you want to get, trim for your inside doors and cabinets, that's a different story, but it's a very small volume. Okay, so this is based on, we've done like 8 years of sampling real-world construction demolition debris, separating out the inorganics. This is the kind of heavy metal loading that you see in a typical construction and demolition debris load. This is basically the 8-year running average. Well, actually not the average, it's sort of like the population points of the lowest that we typically see and not quite the highest we typically see, but anyway, so when it comes to technical development and technology selection for thermochemical conversion technologies, we focus on what I call the A's, B's, and C's: arsenic, boron, and chromium. Why? Because there's a lot of boron, and really nobody knows how it operates under gasification conditions. And then arsenic and chromium are, of course, everybody who knows, understands how toxic they are. They're also volatile, so they tend to actually fly into the syngas, and you have to get them out of the gas before you can do any kind of downstream processing or refining. And you certainly don't want it going out the stack. There's other old school, sort of waste to energy challenges as well. There's still chlorine, and fluorine, and you have to deal with those caustic elements as well in your syngas. So for our technical and project development, we're not designing gasifiers. We partner with companies that have the right kind of like technology fit for the feedstock, for the particular community problem and waste stream we're trying to solve. What we have done is develop some of our own intellectual property specifically around heavy metal sequestration and control. So we're able to take real-world construction and demolition debris with those heavy metals from the treated lumber, gasify them under typical fluidized bed gasification conditions, and still sequester the heavy metals into the ash and keep them out of the syngas so that we don't poison downstream fuel refining catalysts. We've done all of our sort of pilot scale testing at the University of North Dakota Energy Environment Research Center on their fluidized bed gasification pilot plant. We're able to go from waste, real world waste in, all the way to hydrogen out. Our focus has been on hydrogen because in order to make really any other kind of transportation fuel, you need hydrogen. You need hydrogen for hydrotreating fats, oils, and greases. You need hydrogen to be able to combine with your syngas to make methane for renewable natural gas, or any other kinds of gas to liquids technologies. You still need hydrogen for oxygen removal to make a hydrocarbon. So I'm showing them some pictures here. So this is some testing that we did last year about this time, some real-world waste truckloads, hand-sorted, because our MRF isn't built yet, and then actually shipped to North Dakota from Honolulu. Our C&D waste recycling partner calls it the most precious rubbish on the planet, and fed into the gasifier there and made hydrogen. We've got one more trial for that scheduled to go in September, this coming September. Okay, so on gasifiers, I decided that since we've got enough risky things going on with kind of a novel feedstock that isn't well understood for thermochemical gasification. So after over a decade of searching, we selected EQTech out of Barcelona and their fluidized bed gasification system. Why? They have 100,000 hours of operating data on a commercial plant at this exact same scale and on a woody feedstocks. The only different thing that we're doing is, again, that heavy metals and the other kinds of contaminants that you come to expect with construction and demolition debris. So a little bit about the carbon intensity. This is a consultant that we hired, SCS Global, so their greenhouse gas life cycle analysis for our notional project, after our FEL2 engineering of our project in Honolulu, this is the estimated greenhouse gas life cycle analysis. One of the things that we do for our Hawaii projects that is probably unusual to you is we also compare to natural gas and hydrogen made from petroleum. The reason why is because the natural gas that is sold in Honolulu today is actually made from naphtha. It's basically, it's not steam methane reforming, it's steam butane reforming. It actually has a much higher carbon intensity than just regular, even fracked North American natural gas. And we don't get below zero, but we do get very close to zero. And this is without any ancillary measures. So this is without carbon sequestration. It's without counting the carbon that's left in the ash. It's without any CO2 utilization, even though those are options. What I wanted to do with this initial greenhouse gas life cycle analysis is just what's the base case for the core process? What does our CI end up being? Okay, so now we'll start to get into projects. Again, our focus on our home turf is the city, county of Honolulu, the existing C&D landfill, former clients of ours. We have a very good working relationship. In fact, they've helped to fund some of that greenhouse gas life cycle analysis. But they're just not in a great area. You can talk in environmental justice, there's kind of a chicken and egg thing. Are the low-income people around the landfill, or is the landfill near the low-income people? Really, it's because of land values. This particular area of Oahu is dry. It has no fresh water, so it was never valuable for agriculture. So, and it's only got one road in and out. So for the people who live in that neighborhood, their commute is about 45 minutes just to go those 9 miles. And every third vehicle on the road is a 2.5-ton trucks taking stuff to the C&D landfill. So we have a lot of community support for basically stopping all that activity. And all of the construction, demolition debris, and MSW generated in the entire city and county of Honolulu is on that road going to the 2 landfills. And they're all passing the industrial park on their way. So what we're doing is basically just moving the activity to the industrial park. Okay, so, and where is he? Anyway, the consultant who presented yesterday actually did a fantastic slide on our Smurf project. We do call it the Smurf. It's little. We plan to paint it blue. And it's our sustainable materials recycling and fertilizer facility. The extra F is really just uniquely a Hawaii thing. Again, it's sort of addressing some of the local challenges. Fertilizer costs 50% more in Hawaii just because of transportation costs. And half of it is just chicken shit in a bag. And we can do that. You know, we can put chicken shit in a bag in Honolulu. We don't need to import it across the Pacific Ocean. I'm sorry, did I say that out loud? Okay, so this is the Smurf. I actually really like your slide better, so I'd like to get it from you. So we have a small community project offering. That's our 50-ton a day gasification project. The Smurf that I just showed. Actually, I should go back to it. I'm sorry. Nope. Okay, nope. I'm clearly hitting the wrong button. Thank you. Please do. All right. Got a sneak preview. Okay, so the Smurf is 50 tons a day. That is like about the same waste stream as you would get in like the community of Kauai, which is a population of 80,000 people, 200,000 if you include the tourists. Okay, so it is economically viable because of the fertilizer product. It's not quite enough throughput under U.S. and even Hawaii economic conditions It's profitable, but barely. It's a good investment once we have these other value-added processes. So again, the fertilizer is kind of a uniquely local thing. This is the kind of the 50 tons a day is also, we've talked about sort of with our C&D recycling friends on the continental U.S. siting at or near their MRF to be able to self-power their MRF. So 50 tons a day of dry waste feedstock generates about 1 megawatt of power and another megawatt equivalent of thermal energy. Okay, then we have a larger product offering. This is the one that's actually called Aloha Carbon. This is the focus on fuels. This is where I originally focused because my focus has been on making renewable fuels. That's what my company has done as a consultant for 15 years, is advise on how to manufacture renewable fuels. And we decided to just get into the business of actually doing the project development ourselves. So this is 500 dry tons a day of feedstock in gasification, again, fluidized bed, using 2 to 3 modules, so about 150 to 200 ton a day modules, in order to get that 500 tons a day of throughput. That's actually sized at a quarter of the feedstock flow for the market, because we don't ever want to be in a position of being starved and having to beg for feedstock in order to keep a 24/7 plant up and operating. The estimated output of that is about 6 million cubic feet a day of renewable natural gas, which for Honolulu is about 20% of the utilities demand. On the continental U.S., it's not quite as significant, but still pretty good for RNG supply. Okay, so starting to get to a little bit on project siting. Again, siting is important. So this is where we start to get into the community acceptability. Again, the focus was to bring, the waste out of a residential neighborhood and out of a Native Hawaiian homestead area, bring it into the industrial park. This is an expensive land. That's why I had to add the fertilizer plant, just to cover our operating costs. But for our Smurf and Aloha Carbon plants, which are going to be co-located on the same parcel, in Campbell Industrial Park in Kalaeloa. We're between 2 petroleum refineries. We're 2 blocks away from the city's MSW incinerator, our waste energy facility, which is operated by Covanta. We're across the street from AES's former coal-fired power plant, so we also get energy community tax credit opportunities for this particular project. And we have 2 blocks to go to an independent power producer that's planning on putting a natural gas or RNG conversion into their turbines, or we can go another block and connect into the Hawaii gas transmission pipeline. So community engagement is important. All the technical stuff is fantastic. The feedstock, the project development, none of it works if nobody will actually let you build a project, or if you get sued out of existence, either before or after actually building the plant. And Hawaii, unfortunately, has a lot of examples of projects getting built, permitted, then built, then starting to operate, then getting sued out of existence by community opposition. So, and I think it was one of your jokes last night, like you want to be on a street corner saying, honk if you love biogas for 3 years. So we actually had to do some kind of innovative community engagement. So we actually started just buying tents at farmers markets and having it be a community survey opportunity. So people would be walking around with their kids and their plate lunches and their fried chicken, and our tiny little team, including me, would be out there, hey, would you like to come in and share your opinion about landfill diversion options? And they would just stop, and kind of eyes would get really big, and then shoot into the tent. Give me a pen, where can I sign? So when the time comes that somebody tries to raise a stink, hey, we didn't know about this project, we have a lot of people, elected representatives, regular community members, we've got pages and pages and pages of signatures, hundreds of survey respondents. No, we've been out in the community. This was actually something to solve the community problem. We're not project developers trying to find a place to site our project. This is grassroots. And so I aspire to also doing that in other locations as well, because most investors, including our prospective investors, like to see a pipeline of projects, not just a one-off. Okay, so here's how to reach me. Again, Joelle at alojacarbon.com as opposed to simonpietri.com. And I've also got some of our other team members here if you've got specific questions for them.
Jolie, thank you very much. It was very entertaining, and I'm going to reiterate, project outreach has been key to success in California, and we did stay out on street corners for a long time and coffee and donut days and build that community support and eliminate that opposition early and reach out. The next speaker is Dana Charles, co-founder of Veriflux. And I think we're moving well on time, so I'm going to talk to them, and if we'll have other questions. Welcome. Thank you.
Thanks. Awesome. Thanks, everyone. So we're going to talk about tracing waste energy from point of collection to fuel production and beyond. A little bit of background on me, and then I'll jump into a little bit on Veriflux. So I actually did not start in the waste industry. I started in national security, working for the U.S. government. And about 10 years into my career, one of my college buddies reached out and said, "Hey, what have you been up to these days?" I was like, doing some work. Why? And he's like, "Well, are you interested in getting into the waste space?" And I was like, "No, not really." He's like, "Well, you might be interested. There's this thing called used cooking oil that comes out of restaurants, and there's a lot of increasing demand for it. Do you want to come check it out?" And I was like, "No, not really." He's like, "I'm telling you, there's going to be increasing demand. You should come see it." I was like, okay. So I took a trip up to New York, which is where he was based out of, and we went to one of his facilities. And I walk in, and I go, "What is that smell?" And he goes, "It's the smell of money." And at that moment, forget the actual smell of the facility, I realized what was happening in the industry, something that I'm sure a lot of folks here have realized in the subsequent years around just the waste conversion side of it. And so together we embarked on converting used cooking oil into a feedstock. At the time it was for biodiesel. A lot of it was going into the industry already, and then more recently it started to go into renewable diesel, SAF, things like that. In the time period that we were doing that, we realized that there wasn't really good data around where our product was coming from. So we would buy used cooking oil from a lot of third-party suppliers. It's a lot of independent waste collectors in the supply chain. And we would have quality issues. Free fatty acids would be high. Now more and more people care about metals. At the time it was free fatty acids. And we would try to identify where is this coming from. And it wasn't just a particular supplier. It might be a particular restaurant because, and this is going into the weeds a bit, but depending on the bin that's in the back of the restaurant and the amount of time that the waste is sitting there, it starts to transform the quality of the product. And so we wanted to start to identify those sources. And we thought to ourselves, well, naturally, our suppliers should be able to tell us where this product is coming from. They couldn't. And the reason why they couldn't, and again, I'm sure you're all familiar with this, is when we're talking about a lot of these raw materials that ultimately get converted into feedstock on the waste side, they're coming from restaurants, et cetera, and a lot of those initial transactions are happening, for the most part, on paper. Maybe someone writes it on a slip, takes it back to their office, eventually it gets inputted into a computer system, but that's days, weeks, months later, and so there's just really not a lot of quality data around where this stuff is coming from. Now, this is 10, 15 years ago, so it didn't particularly matter other than the quality issues we were experiencing until 2020, when the EPA announced that they were going to enforce their record-keeping requirements within RFS, within the Renewable Fuel Standard. And that's when we sort of had this aha moment. We had been building our own internal system. We sort of had this aha moment of, wow, the EPA is going to want records for where all waste streams originated that then get converted into the fuel standard. How's anyone going to be able to comply with this? And then subsequent to that, California added their requirements for LCFS and so on and so forth. So that's when we founded Veriflux. We founded Veriflux in 2020. That's a bit of our origin story. We got funded by the EPA in 2021. I'll talk about that in just a second. We launched commercially in 2022. Today, we're working with supply chains from over 400,000 points of origin in over 20 countries, encompassing 950 companies. On average, we're tracing about 70,000 metric tons per month of renewable feedstocks. Our bread and butter started as used cooking oil, but we've now expanded significantly, and the output is no longer just our traditional area, which was biodiesel and renewable diesel, but now it's renewable plastic, sustainable aviation fuel, RNG, and a lot of other applications. In the beginning of this year, I wrote an article that said 2024 is going to be the year that traceability goes global. And the reason why I wrote that is because more and more, I have access to a lot of data, right? So I can see a lot of different flows. And more I was seeing that a lot of these supply chains that were dealing with these materials were going into different markets than perhaps you would have thought. You'd have product that was coming into the US that ultimately was ending up in Europe. And because of that, you ended up with a lot of jurisdictional challenges around compliance. And I'll talk to what that is. But then on top of that, there at the same time, so you've got these two tensions. You've got markets moving based off of commercial dynamics, and then you've got this emphasis on circularity. And so at the same time as stuff is moving more global, stuff is also becoming more local. And each of those require that same degree of data. To be able to prove something stays local, unless you have a very linear supply chain, you need the data to be able to substantiate that claim. Similarly, as stuff is moving globally, you need the data to be able to know what market it came from and what market it's going into in order to be compliant. And so when we talk about these different compliance regimes, the one to naturally start with is the RFS requirement. And so under RFS, Title 40, Part 80, 1454, J12, if anyone's curious. There's this requirement for documents demonstrating the amounts by weight purchased of waste oils, fats, greases for use as a feedstock in producing renewable fuel. Additionally, you need documents demonstrating the location of any establishment from which the waste stream came from or was collected. So that's kind of the initial requirement that kind of dictates RFS. So that's one requirement. And then as part of the set rule that the EPA announced last June, they kind of codified three different approaches for how you can do record keeping. There's the traditional approach, which is that the RIN generator holds the records. So imagine that you've got these really robust dynamic supply chains that all go down to a producer or an obligated party that's going to make fuel and generate a RIN. They have to have all those records on hand when they generate the RIN, according to the traditional approach. The second approach is what's called the alternative approach, which is that they get every single person in their supply chain to register with the EPA. Again, imagine that, right? I'm going to go to all my suppliers, half of whom probably don't trust the government, and I'm going to say, please register with the government so that I can track your stuff, right? Or the third is they can nominate contractors or third parties like software to hold their records for them. So what was some of the outcomes? Well, the first is naturally there's been increased confusion in the market. What does it mean to be compliant with the EPA? What are the documentation requirements? And I'll get to it in a little bit, but there hasn't been a ton of definition around that, and there's a reason why. So that's on the federal side as it relates to RFS. Then on top of that, you've got the Inflation Reduction Act, and you've got the guidances that were released by IRS for 40B and pending 45Z. California, their original proposal to amend LCFS, the more recent one that came out 2 days ago. New Mexico, Washington State, Oregon, Illinois, Nebraska, you have all these additional markets that are popping up with either LCFS, SAF credits, things like that. On top of that, then you've got Canada and Canada's requirements. And so Canada's requirements are slightly different from America's, of course, they have to be. And so with that come an actual quantity formula for how you calculate what feedstock was where at any given point in time and how you can allocate that on an allocation basis, and what the eligibility criteria are for different feedstock. So slightly different, and those slight differences matter, and I'll get to that in a little bit. And then you've got Europe. And so Europe's approach for a lot of these, specifically biofuels, was to set up a database. They call it the Union Database for Biofuels, or UDB. It's a nightmare. It's terrible. Basically, the idea is that everyone's going to report into this centralized database. The EU has kind of a unique problem. They've got member states. They can't all agree on policy. So they got infighting among member states. Then they've got fighting from the private sector. But all that lends itself to this database that all transactions are supposed to be reported to. So I said 2024 is the year that traceability is going to go global. And what I mean by that is when you are picking up waste, when you're collecting waste, used cooking oil, any kind of biomass, whatever, you're picking up some sort of waste. And then you're going to transform that waste. Unless you know exactly where it's going, right? I know it's going to go down the street to this production facility to be converted into this. Unless you know that, then you have to somehow grapple with the fact that your product, your feedstock, can end up in a finished product that can end up in different states, in different countries, and suddenly now your product has to be compliant across all those markets. To put a fine point on it, you could collect used cooking oil here in San Diego, and because the finished product, sustainable aviation fuel, renewable diesel, plastic's a bad example, but some other product, because it ends up in Europe, you have to report your collection from the McDonald's down the street to the union database in Brussels. And so that's kind of the inherent challenge. And then on top of that, right, again, when we're talking about these supply chains, there's just inherent challenges within each of them. First is a lot of them depend on paper from the start, so they're not digitized by nature. A lot of them are liquid or other kind of materials that you can't, they're not easy to tag. So, the idea of tracing it becomes an exercise in how do I capture a batch or a series of batches or things like that. These supply chains are multi-stakeholder. They're often in competition. On one day, you're selling your product to someone that the next day they're competing in the same market against you. And so how do you feel about sharing your data of your customers with them, right? It's a major challenge. And all this adds an operational burden. And so if you look at used cooking oil as one example, what we're basically doing is providing a data pipeline underneath all of that to help everyone across the supply chain to facilitate that kind of connectivity. And in the process, helping them to identify what markets their products are compliant with and what additional data they need to gather, a lot of which they already have, they just don't realize they have it, in order to be compliant within different markets. And I'll give two data element examples to kind of highlight this point. The first is a national trade register ID, as Europe would call it, or as we would call it an EIN, right? Every business has one. Well, in the US, there's no obligation for an EIN to be a part of any kind of traceability. EPA doesn't need you to record an EIN when you do a collection. The Union Database for Biofuels does. So in order to be compliant, technically, and they might change this because I've given them a bit of hell on it because I think it's crazy that you have to record an EIN for McDonald's in order to record a pickup. But regardless, in theory, if you're doing a collection and you don't have that EIN, then your product won't be eligible into Europe. And again, you may not know that product's going to Europe until you get a call 6 months later from someone all the way downstream that consumed that fuel in Europe saying, hey, I need this to be submitted to the Union Database. And you're like, I don't even know what the Union Database is. What are you talking about, right? So these are the dynamics that need to be managed. The second is the collection record. So subtle difference, but in the US, you have to record each individual waste collection. So I collected, X amount of pounds on this day. I collected X amount of pounds on this next day. For a lot of the European standards, you record annual collection volumes. So you'll say, I collected this much from McDonald's over this period of time. Again, subtle difference, but how you store that data, how you manage it, et cetera, will then impact the ability to be compliant. And all of this within an environment where the government's actually starting to crack down on this because of a lot of fraudulent feedstock streams. A lot of them coming into the US from overseas, but they're taking US tax dollars as part of these programs. And so the government is gearing up to enforce this, as is Canada, as is Europe, as are the states as well. And so that's kind of the environment we're in. Now, I mentioned that there's a lot of lack of definition around some of these regulatory issues. So one thing I'll point out, in theory, when you're talking about a regulation, you've got the rule, you've got the guidance, and then everyone in the commercial world just follows that guidance. Nice and linear, really easy. In reality, when you're dealing with governments, this is kind of what it looks like. They issue a rule, then depending on which office within the government you're talking to, they'll give you different guidances. EPA is a great example. Their policy office will give you a different guidance than their enforcement office. Then, depending on which consultant you're talking to, who's talking to those offices, they'll give you different guidances. Then the regulated parties, the ones that actually have to adhere to this, are then going to get all of this from their auditors, consultants, et cetera. And then when they go to industry, now suddenly you're hit not with one, but with 15 different interpretations of the regulation. And so again, now we're going from I'm just picking up waste to I need to pick up waste, I need to comply with all these different government, federal, state, international regulations. Oh, by the way, I'm getting 15 different interpretations of each of those. So the way we handle that, the real question is what do you do when you're getting that? And the way we handle that is a couple ways. First is we allow you to capture and authenticate the traceability of the feedstock from the point of origin, and we try to make it as easy as possible, because if you add any kind of burden to that first mile of effort, it's going to become really hard for folks to comply. We give multiple mechanisms for data capture. This is what our mobile app looks like when someone's doing a collection of a particular waste type. We allow you to manage different transactions, and as you're flowing that product, kind of manage it within a single interface. And as part of that, we allow you to see what different frameworks you're complying with, both the set rules of those frameworks and also the different interpretations. So if you get an interpretation from an auditor, let's just call it KPMG just as an example, you could say this is KPMG's interpretation of RFS, and you could see then, okay, am I complying with their interpretation? Am I complying with this other person's interpretation? So on and so forth. You can manage inventory and assignment of product. You can manage accounting, different accounting methodologies, first in, first out, and so forth. At the end of the day, this allows the product to flow through and produce end-to-end traceability, both of the chain of custody and of the points of origin. And in the process, and this is what's really novel, is then it allows you to have proof of sustainability downstream. So when the folks downstream are making claims, they can have proof of sustainability of those claims and proof of circularity. And so we did a big pilot program with New York City a couple of years ago. And as part of that pilot program with New York City and Waste Management, we were actually able to trace waste from across the 5 boroughs that got collected that ultimately ended up in RNG that got used within the city. And that whole circular supply chain, we were able to not only map it, but we could actually substantiate it, every single waste bit by bit. And that's kind of the end product of where this is going. And so whether that ends up in a regulated market, where at some point New York City requires there to be an X percentage of fuel that's of a local nature, whether that ends up in a voluntary market, being able to trace it has those added benefits. And so when we think about what the implications are for the waste energy market, the first thing I'd say is there's going to be continued confusion around these requirements. That much I can guarantee. Part of that is going to be because the EPA is going to continue to have these issues around definition. Part of it is because there's just going to be a lack of understanding within the marketplace of what's ultimately required. There's unfortunately a first mover disadvantage in a lot of these cases. Like if you're the first person to become traceable, you're adding a burden in a marketplace where the market yet hasn't defined a premium for being traceable. Now, you may ultimately decide that's an investment worth doing because of reputational risk, compliance risk, et cetera. But until your downstream buyers fully value what you're doing, you kind of have a first mover advantage because you're adding those additional costs. And so that's been hard, but that ultimately is reducing over time. This leads ultimately for an increased demand for single source feedstocks, right? The more you can narrow that supply chain, the easier it is to trace it. But that's not sustainable because those get eaten up pretty quickly, and then you have to look to the more complex dynamic supply chains. And I should add, California is shifting more and more to a dynamic carbon intensity score for these supply chains, which is going to make it all the more complicated and all the more important to have traceability as a result. And just to conclude, as a result, you're going to then have increased demand for traceable supply chains and feedstocks in order to reduce regulatory risk, substantiate sustainability claims, and ultimately prove out circularity. If you're interested in learning more about Veriflux, that's our website, that's my contact info, and look forward to your questions.
Dani, thank you. And we think it's complicated now, so I've always learned over time, complicated things made simple, and the traceability, the EPA has a real reason for doing that, because in the early days of the biofuels, just the amount of fraud lost public support. So integrity in the process builds all that support. Our next speaker is Hartmut Bendfeldt, and he'll be speaking on the waste to fuels and energy recovery through his equipment and technology. Thank you. Welcome.
Good morning, everybody. It thinned out a little bit over the last couple of the hours, but we're getting towards the end of it. So I'm going to speak a little bit about waste to fuel, energy recovery, basic preparation of fuel for all the different technologies that we see out there, gasification, and so on. So who are we? So my company is called E-Factor3, and the 3 E's stand for environmental engineering and equipment. I started the business on a lucky number, 08. And we offer single machines as well as complete processing lines for plastic and waste processing, recycling industry. Not only do we sell the equipment, we also service it. So we're a one-stop shop with a location in Charlotte, North Carolina. That's me. I'm not going to read this. But I've been in the industry of recycling, size reduction for the last 30 years. I've been doing project management and sales of equipment during that entire time. The industries that we serve are very broad. Waste to energy as a general term, which could be incineration, gasification, and other things, alternative fuels for the cement industry, lime kiln, regular waste processing and recycling, plastic processing, and plastic recycling. These are kind of the industries we work with, and today we will speak predominantly about the processing of waste to fuel. Here are a couple of examples. Again, all of the equipment that we represent or sell give us the ability to put complete systems together. So it starts with pre-shredding, goes through screening, sifting, separation, fine shredding, cleaning, dry or wet, granulating, extrusion, conveying bunker systems, systems integration and installation, and also mobile equipment. So in order to properly design, of course, a processing facility for waste to fuel, there's a couple of things that are very important for us to know. Is what is the source of the waste stream? What's the composition of the waste stream? What's the density? What's the final fuel specification for the downstream process? And the more homogeneous the input material, the simpler the process can be. So if we think about the most complex stream of material that needs to be processed is MSW or MRF residuals, because it's a pile of a lot of different things. What is a lot easier is the commercial or industrial waste streams. And this would be a typical SRF, PEF for the cement industry, for example. And then fuel for the advanced recycling process. So we'll dive in a little bit more into the process steps. So typically the first step of prepping material for fuel is a pre-shredding process where you can process a large variety of different materials, from bulky waste to commercial industrial waste, MSW, C&D, and things like that nature. It's very diverse in the application. We have stationary as well as mobile equipment that we can utilize for it. And this would be kind of the technology we would be using for it. So it can actually deal with heavy contaminants. It can also cope with big surprises that we see in MSW. Unshreddable items are very common in waste. It gives us a very even distribution for the downstream separation technology. It is very low cost in operation, and it can even deal with complete bales or rolls of material that are fed in, including the wires. This is the same technology in mobile. Sometimes we actually bring these units to our clients for a demo. They can also rent it to test it, to really get an idea of how this technology works for their process. And then typically the next step in the process would be the ferrous removal with inline magnets. And then, depending on the process, we want to remove fines, inert organics. That's typically happens through screening technology. There's a lot of different screening technology out there. We offer a technology that can in one step do 3 fractions. It uses a hexagonal disc design to prevent any wrapping from film. It doesn't produce the typical alligator tails that you sometimes see from thermal screens. And it gives a superior agitation of the material, so you really shake out as much of the loose inert as you can. This is a picture of the equipment. The left picture shows a mobile equipment, and the right is a stationary piece of equipment. These are modular machines, so they can build exactly to the specification in segments of 2 meters and 3 meters combined. Now, typically, at this point, the material still can contain heavy contaminants, like glass, rock, wood, non-ferrous metals, and we can remove that with the technology called a wind sifter. So in a wind sifter, you basically have an airstream that blows. This is a pointer. You have an airstream that blows through the material. The material is fed into the system with a wide conveyor, and an airstream will blow through the material against a separation drum. So your heavy contaminants will fall out this way, and your light materials will go on to the next downstream step. Now, in some cases, it could be that the process actually wants you to separate it into 3 fractions. A heavy fraction, which would be a contaminant, a medium fraction, which would be lower BTU level type of material, and then a very light fraction, which would be just a film plastic. That is, for example, what we see in the cement industry as SRF. We see the difference between rigid materials and film. The film is typically utilized in rotary kilns. The heavy stuff is used in the calciner, typically at a larger size. So this shows the principle. Again, we're blowing through it. The medium material will settle on a conveyor. The light material settles on top, and we separate from there. We suck off the light film, so we get a very good separation of just the light film. And then in addition to that, the next step would typically be optical sorting. That will be utilized to purify the material, remove PVC or other halogenic type materials from the stream. Also gives the ability to, of course, shoot out recyclable material that has more value as a recyclable than a fuel. And gives us also a reading of the BTU level and the moisture level in the material to analyze the fuel quality. The next step would be a secondary downsizing, typically. In the cement industry, we're typically looking at a 2-inch minus, a 1-inch minus. In the advanced recycling world, we typically see that we want to get rigid material down to about a 1/2 inch minus, and film typically needs to get down to about 1 inch minus and then needs to be actually densified for the process. So in this case, on these shredders, we use a multi-edge rotor that creates minimal friction to make sure that we don't have to cool the machine when we're shredding sticky film. It comes in a large variety from about 1.4 meters to 3.2 meter wide. The biggest unit can process up to 23 tons an hour at a screen size of 2 inches. And the next step would be, if we have to densify film plastic for transportation and process requirements, we would utilize a pellet mill, like in the Mandescal. With that unit, you can take the feather-light material of film that's shredded to a density of about 15 to 20 pounds a cubic foot. That is typically required for a lot of these chemical processes that we see. So this is what a fuel pellet would look like. These are about in diameter about a half an inch, so I have no scale on it, but this is, again, for transportation purposes and for feed mechanisms, very important. To tie this all together, we need, of course, conveyors and bunkers. And we can also supply complete alternative fuel delivery systems. What you see in this picture, this is actually a conveying system that feeds from a receiving dosing bunker to a, in this case, heat tower in a cement kiln. This is an example of a complete MSW processing plant to fuel for a gasification process. And this is designed for 500 tons a day. In this particular case, the customer is diverting out the organics at the front end and then puts it back together in the back end, because their process can burn the organics as well. But we are separating out, let's try to see if this works. We're separating out metal here, non-ferrous metals here, separate out heavies here, and then have optical sortation, final shredding. And on this line, we're running the organics, clean out the organics with the wind sifter as well, use optical sortation, and then recombine it all into a bunker system to the downstream process. During the days of the conference here, I also recognized there's a lot of talk about the organic and anaerobic digestion. So just want to point out that in addition to the equipment that you just saw in this presentation, that we also offer the packaging equipment to recover organics and separate out the plastic or the metals. And certain processes like to have dry and clean material. So we also offer a technology that we call a dry cleaning technology. With this, we can clean up contaminated film or rigid plastic to remove any moisture and residual dirt. So these are kind of the partners that we have. And that was kind of my short presentation about the technology that we offer. Thank you.
Thank you, Hartmut. Next is Eloy Flores, and we'll go from there.
Hello. So hopefully last but not least for the morning session. But yeah, thank y'all for for sticking around. My name's Eloy Flores. I'm the director of the of the chemical engineering department at Southwest Research Institute in San Antonio, Texas. Yeah, and I'm going to talk a little bit about what we do and some of the areas that are related to this conference. So about Southwest Research as a whole, we have about 3,000 employees. We're located in San Antonio, Texas. We're on about 2,100 acres. We're a 501(c) nonprofit contract research organization. We have no government affiliations. We have no endowments. All of our projects are fully funded by our clients. And we have, out of any of the other nonprofit organizations similar to ours, we have the largest technical breadth of all of them. Also, the amount of commercial work we do, I think, is much higher compared to a lot of the other organizations where they focus primarily on government funding. We do have a lot of government funding. We're funded about 50% government, 50% commercial, and that shifts depending on who's in office. But so here's a list of the technical breadth. And again, so we do everything from deep sea to deep space. So the New Horizons Pluto mission is something we've done. We do lots and lots of other missions, and NASA primarily is one of our largest government funding agencies. But we also have mechanical engineering groups. We do artificial intelligence, machine learning, AI, you name it, we do it. And so we're able to take that technical breadth to any project, and specifically in the area where we work in process development. So again, in the chemical engineering department, we work on almost any and every type of process you can imagine. But here we're going to focus on some of our thermochemical processes that we've had the opportunity to work on. And we have a long history of supporting our clients in everything from heavy oil to coal to biomass, waste plastics, you name it, we're doing it, especially right now in this whole sustainability era. Probably 95% of our work is related to renewable fuels, renewable chemicals, pyrolysis oils, carbon capture, all in that space. And MSW is something that we've kind of have done a little more recently. So we're all here for the opportunity that I'm sure everyone knows now at this point, especially at this stage of the conference. But yeah, there's tons and tons of waste that's available, and the U.S. only recycles a very small amount of it, or uses a very small amount of it for energy. So there's tons of opportunity. Other countries are doing much more. So again, we all know this stuff too, right? There's expected rate of return, and it looks to be a growth area. Kind of small, if you ask me, but it's still a growth area. The interesting thing, I think, in these charts is this thing here, which I don't know how to point, but that's okay. But you can see where it flatlines. This is actually the amount of municipal solids being processed, or the megawatts, or the fuel, the energy capacity that's being processed. And you can see it's kind of flat. So that's interesting. I don't know why that is, but maybe you guys know. But we are seeing an increase in other things which we primarily work in, which are the renewable fuels like renewable gasoline, renewable diesel, and of course jet fuel. So the market's there, and we're all pursuing it. Again, there's more market incentives from the government, especially in the U.S. The U.S. is dumping tons and tons of money into this, which lots of folks are trying to do. They're also adding more credits for waste. So existing technologies, primarily these focus around pyrolysis and gasification. Removing impurities is a big deal, and emissions are obviously a big deal. And then there's things like tarring and fouling that occur in a lot of these technologies. And I guess I have some particular stories, but ultimately what we see happens with the tarring and fouling is you can mitigate the tarring and fouling. However, the feed rates that are necessary to make these processes economic require you to push it to the point where the tarring and fouling does become an issue. There's also fermentation, anaerobic digestion. So just looking at waste to energy, there's a lot of plants that were up in the Northeast, and most of these are being shut down. So I know they mentioned here that community advocacy and all that is very important, and that's a huge deal because we've been part of at least 2 projects that were at the point of commercialization, and both of them were shut down by picketers, basically. So even though it made economic sense and everything else, If the community doesn't support it, then it's a dead deal. So, an important thing. Okay, so thermochemical conversion technologies, most of y'all are probably familiar with these things, but you take some type of feedstock like biomass, municipal solid waste, you put it through some process that requires energy, typically a catalyst, and almost everything requires hydrogen because most of these feedstocks have low hydrogen content. So, and you're trying to make higher value compounds that typically require more hydrogen. You go through this conversion technology process and you end up with some type of gas, typically hydrocarbons, or you could go straight to syngas. There's typically a water, maybe a bio oil or pie oil. And then there's ash and the other stuff that comes with that. So working with a lot of these companies, like we work with companies now that even have huge offtake agreements, and they have gotten, again, I don't know how the pointer works, but they've gotten to the point where they're producing material, maybe even Fischer-Tropsch liquids, waxes, but they're committed to providing jet fuel. So that's very interesting for us to see that. Obviously, we don't tell people about that, but so many of our clients forget about the cleanup step. They forget about the hydroprocessing or the isomerization step that needs to happen for Fischer-Tropsch waxes. And they just say, we're making liquid, and that liquid is a fuel. You're just going to stick it in your car. So because of that, I think we see some projects that end up getting they have setbacks because of that. So that's an area where we tend to specialize. If anything's been converted to jet fuel, it's probably come through our facility. We've turned chicken fat, algae oil, like you name it, municipal solid waste, Fischer-Tropsch waxes, all that we've converted to jet fuel, diesel, and gasoline. And then I mentioned the fouling. That's another area that's very common across industries. So we've started a consortium, and we're working with industry to come up with non-competitive solutions, I think, to try to solve these issues across the industry. We also make chemicals, and I mentioned the fuels. So the opportunities here in the energy sector, we work a lot with companies that are working on electrification, so lowering the carbon footprint using renewable power. That's a big area where we've worked on integrating different types of process heater technologies or specific catalysts, how you heat your equipment, different things. Hydrogen sources, we work a lot with low carbon hydrogen production. Electrolysis has probably been done, but a lot of companies right now are looking at pyrolysis as probably the main competitor to SMR with CO2 capture. So there's a lot of work in that space, and we see a lot of promise actually in that if we can find a market for the carbon. And anyway, but that's a whole other thing. And then catalyst development, we work a lot with companies who are developing different catalysts to help improve these processes. And then I mentioned the cleanup step, so everything from membranes to solvents and all that, we work a lot with those companies as well. So we had the opportunity to sit down, and we don't really we don't have really a lot of internal funding, but every once in a while we get to do a little few projects on ourselves. So we sat down and we said, okay, if we had a black box that solved all the problems with pyrolysis and hydrotreating all these renewable fuels, what would we produce? And we came up with this high pressure fluid bed concept where basically it allows us to deal with the catalyst issues. So for example, in hydrotreating, you have a lot of fouling, the salts and things like that cause trouble. Well, with the circulating fluidized bed, we can mitigate a lot of that because we can remove the salts. We can do activation in another loop on the circulating fluidized bed. We mentioned metals, so another thing we can do is we can put scavengers into this fluid bed that would grab the metals, and we've done studies where we've done 1,000-hour studies doing metal accumulation with certain types of feedstocks, and we can see what the impact is on that catalyst. So that's how we came up with this concept for this high-pressure fluid bed, and we've been using it now for a couple of internal research programs. One is with Monterrey Tech in Mexico. In this case, they had a process where they were producing a biochar, and they wanted to find a way to continuously produce the biochar rather than just doing batch pots. So we offered the circulating fluidized bed as an option, so we're able to actually generate the char. Char comes out overhead through a cyclone, and we can continuously produce it. So we did some studies on that. And the main objective of their char was to produce a CO2 absorbing char. And ultimately that failed, but they've come up with another solution where they're taking a renewable source from shrimp to basically apply an amine type molecule to the carbon, and then that does increase the CO2 affinity dramatically. So But anyway, then the other one is the city of San Antonio. So the city of San Antonio is great. They don't have any money, but they have waste, and they get to decide where that waste goes. So we've had the opportunity to work with them, and we did a conceptual study, which I'll talk about right now, to look at converting their municipal solid waste. Primarily, their interest was, can we convert the municipal solid waste into a liquid fuel like diesel that we can then put in our fleet? And that was kind of what we looked at. And we did some testing in the fluid bed to look at that. So here's this is our lab scale. Again, this is, TRL 2 or something. I mean, it's really low level. There's a lot of issues with high pressure stuff. It's not as trivial as anything else. But we have like 2,500 pound flanges here, and this is our high pressure fluid bed system that we use. We can use 2-inch, 1-inch diameter. We can do solid feed, liquid feed. And currently we've tested things like polyurethane, MSW plastics, and pecan shells, and I think corn stover and a few other things. It's a fast pyrolysis process, so it's a short residence time. We use sand, FCC, and hydrotreating catalyst to test effects of pressure, temperature, and feedstock composition. We like polyurethane actually because it has oxygen and nitrogen. So from a bio-reference source, we can look at removing oxygen and nitrogen. So this is the one with the city of San Antonio. So here originally we were thinking we were going to do gasification and try to get a Fischer-Tropsch synthesis to happen in a single fluid bed. But we really didn't get that far. So all we did was mostly just partial gasification, pyrolysis, and then hydroprocessing steps on the fuels, on the liquids. So again, lots of municipal solid waste. They gave us the municipal solid waste actually sorted already, or did we have to sort it? No, we had to sort it. But we did sort it because we had to remove like the carbon and the organics and the cardboard and the organics and things like that. And because we wanted to specifically look at the impact of each of those. So again, let me go. And then this is the Monterey Tech project where we looked at corn stover and pecan shells. Apparently in Monterey, pecan shells are very prevalent. And there was a concept that perhaps they had a high affinity for CO2 when they produced the char. But we were able to produce char continuously, but like I said, the char didn't really have a high affinity for CO2. So here's some data that we collected. This was a high pressure test. And high pressure here, we only went up to about 600 PSI, but ultimately we go up to about 1,000. And the main point here, which again, I don't know how to use the pointer, but, maybe this is the pointer. Oh, there it is. Well, yeah, so the main point here is that we used the polyurethane, we did the low pressure tests, and we did the pyrolysis, and then we added the hydrotreating catalyst. And if you see the red in these charts, so these are the low pressure test or without the hydrotreating catalyst. And then the red disappears here, which is great because the red is the oxygen containing compounds. So we showed that we could simultaneously do the pyrolysis and hydrotreating in a single reactor. So that dramatically reduces your carbon footprint because you've reduced unit operations, you've condensed them into one. So there's a lot of advantages to trying to do that. And then also I mentioned you can reactivate the catalyst, you can treat the catalyst separately, you can remove ash components, contaminants. So there's a lot of advantages, and that's primarily our focus with the high pressure fluid bed. Yeah, I think I already covered all this, but yeah. So basically the nitrogen is still lacking. We did reduce the nitrogen total in the liquids, but we didn't get it to zero. Like we got pretty close with the oxygen. Let's see. Yeah, we were able to continuously form the carbon. So these are some of the technical challenges with this high pressure fluid bed, and there's a lot of them. But I highlighted the circulation part in red because the circulating loop of the catalyst and the ability to put multiple catalysts in a single reactor or add scavengers for chlorine, for example. So chlorine is real big with Fischer-Tropsch and other applications. It really gives us a lot of flexibility. So we're hoping that we'll continue to develop this technology and advance that. So we did do some techno-economics, but I'm still challenging the engineers because they look too good to me. So we had assuming a 15-year lifetime, we had a 6 years to cash positive and 11% IRR. But I have a feeling that that's not a reality. I think they're missing like the upstream sorting facility and maybe some of the downstream emission reduction. So, but either way, we did do we have a whole model for this. This is for the city of San Antonio. They only produce about 260,000 tons per year of waste, and so we're continuing to work on it. And we at least based on our model, we can produce about 20.7 million gallons of diesel, which is pretty good. Yeah, and then on the emission side, if you take credit for not doing incineration, you can get to basically a negative CO2 balance. So that's good. Oh yeah, here's the CO2 stuff. So again, looking at CO2 from MSW, some of it gets put into biochar, which then is not get emitted. Then there's a biogas that gets produced. We're calling it a biogas, but it's not really a biogas, it's more a pie gas. And then the rest of it goes back into the bio oil. So some of the municipal solid waste comes from fossil fuels, and so that just ends up back in the oil, so it's recycled. Yeah, we can reduce emissions by 26%, not including the 105,000 tons of CO2 we can displace by replacing diesel with a circular diesel. And so here's a test we did for gasification. We used a low temperature gasification catalyst, and ultimately what we discovered was, yeah, the more recyclables and the more organics you put, the better your hydrogen production is. But we did get relatively high hydrogen yields in our product gas, up to, I forget what it was, but it was relatively high. And, okay, so last slide. So looking at drivers, most of them are social. We mentioned the issues with the plants that get shut down. Sustainability, circularity, all these things are pushing all of this. Government policy is getting there, but you heard about all the intricacies with government policy, so I don't have a lot of hope for that. The government is subsidizing a lot of this stuff, but from what I've seen in the 20 plus years I've been doing this, it's not enough to, maybe one company can take off, but it's not enough to really push the envelope. And the ultimate driver that we find is economics. And also, we notice that investors seem to be, I don't know, I won't say they're ignorant, but there's a lot of investment in technologies that come to us that have very low probability of success. But still, people invest millions and millions of dollars in it. But ultimately, if you can make money, it's going to be successful in our capitalist society. And thanks to Vishal and Toby, they're chemical engineers at SWI. There's my contact info. And thanks to the conference people and everybody else. Awesome, thank
you. Eloy, thank you very much. We'll have time, obviously, for questions. Are there what questions do we have right now from the audience? Okay, we'll go, oh, yes, sir. And if you could say who you are and then your...
I'm Kokoasi Pombliku from Tuskegee University. This question is for Joelle. In the presentation that you made, one of your end product was labeled organic and potash fertilizer. Where is the potash coming from, and what's the concentration of potash in that fertilizer?
Okay, so you were asking about the organic and potash fertilizer. That is actually coming from the other waste streams we don't feed into the gasifier. The potash, wood ash tends to have a higher level of potassium in it. That's where the word comes from, potash. In our case, and this is specific just to the Hawaii plant, the Smurf, the potassium is actually coming from that biodiesel refining cake. We have a partnership with Pacific Biodiesel, and yet instead of using sodium hydroxide as the catalyst for their biodiesel refining, they use potassium hydroxide so that we can reuse the potassium as a fertilizer compound. So did that answer your question?
Yeah, but do you know the concentration of potash in that fertilizer, organic fertilizer?
It's about 30% in the salt cake when we get it.
Okay.
Very good.
Yeah,
We have a question right here.
Hey, good morning. Justin Davis with AMP. I had a question for Eloy about how your research and technology actually gets operationalized. Is it purchased by companies? Are there private entities that then monetize the research? Consultants, kind of how best would we be able to learn from you if we wanted to operationalize any of that research?
Yeah, so we don't really develop a lot of our own technologies because we don't want to be competitors to our clients. However, some technologies have emerged from Southwest, and mostly it's people that want to license something and take it and carry it on. But the best way is to do a project with us. If you do a project with us, then, so again, we have access to a lot of know-how and a lot of experience, obviously, but we can't share proprietary information. But we can apply a lot of that know-how and experience to your project. That's probably the best way. I mean, we also have discussions with clients as well, just to give advice. You know, but yeah, project's probably the best way. Yeah, we get to be a fly on the wall for, like, I know lots of venture cap people and private equity investors and bankers, and so it's pretty interesting, all the things we get to see, and the difference between successful projects and not successful projects. At least from my experience, has been the projects that do something versus design and plan and try to make it perfect. The ones that do something tend to be much more successful. In the end, they may not. Like, they may raise hundreds of millions of dollars and build a couple of commercial plants or semi-commercial plants and then be unsuccessful. But either way, that, to me, that they got a lot further than the guy who tried to get it all perfect and never got the feet off the ground. So anyway, but yeah.
Is it okay if I ask one more quick question?
Go ahead, yeah.
Regarding pelletization of plastics, especially low density, is there a good rule of thumb for volume and distance where the economics make sense? Obviously, if you're just taking a truck across the street, it's not going to need to be pelletized, but as far as how far the material is going to travel when the economics make sense to do any densification?
I'm not sure about that. It's not my cup of tea. The reason why often chemical processes need to get it pelletized is that their feed systems don't like to get the feather weight of film. When you have shredded and clean film, you're looking at 1.5, maybe 2 pounds a cubic foot. So it's a huge volume with very little weight. So that's where it helps a lot with the feed system himself. From a transportation standpoint of view, if it is what I know from past experience in the cement world, I think the limit is still somewhere at 150 miles, 200 miles max.
Thank you. Very good. We have a question right here.
This is for Joelle. In one of your slides, you had an A, B, and C coming out of the treated wood, arsenic, boron, and chromium. Is that chromium hexavalent or trivalent?
Okay. So you asked about the nature of the chromium. The short answer is we don't really care. It ends up in the ash. And our techniques are actually to specifically trap it in the ash and trap it in a non-leachable form. So even though there's a high amount of heavy metal, like the arsenic sometimes can be in the tens of thousands of parts per million, so it's really in the percent, but it doesn't leach, so it still passes T-clip for us to be able to dispose in a REC or D landfill.
Well, in the research that we've done, of course, it does matter because the hexavalent chromium will kill you. And the trivalent is in our feedstock, both in animal and human. But it's about a conversion of one to the other.
Well, in some ways, it kind of depends where the chromium is coming from. If it's coming from the biomass because it was naturally uptaken in the soil, it's not going to be in the hexavalent form. And in construction and demolition debris, you just don't have as much of the hexavalent sort of like form factor in the feedstock to begin with. There can be some shifting in the actual gasification reaction, but at fluidized bed gasification isn't that high of a temperature, so you don't get that much different molecular formation. But again, we haven't really done a deep dive on it because we're just aiming for meeting the regulatory standards for just landfill disposal of the ash. We don't make any claims as far as reuse or sale.
Right.
And the arsenic is just as toxic.
Very good. Thank you for the very good question. We have more. That's good. I have a few quick ones. For Hartmut, I've operated plants, been involved with it. How do you get rid of the sand and the grit? How does your equipment survive that?
Sand and grit, we remove it by utilizing screening equipment and can also utilize the dry cleaning technology if we're talking about agricultural products. Now, there is a significant wear by this material, there's no doubt. Utilizing the right methodology on the equipment helps, hard facing helps, but in the end of the day, sand, glass, and earth will eventually tear up equipment.
Very good. Well, that's an honest answer. I haven't found anybody who can get rid of grit very easily. Dana, what is the cost of compliance, and do you do any QA/QC as an additive for a value-added step for your business proposition?
Yeah, so the cost of compliance, when you look at the supply chain as a whole, for the most part, the liability lies downstream with whoever is in the regulated market. So they're the ones that bear the most cost, but invariably they're going to then push that cost upstream through commercial contracts to their suppliers. So the cost kind of gets borne across the entire supply chain, and typically you're looking at not just the invalidation of whatever the regulatory credit, RIN, et cetera is, but also then fines that might come from that. Not to mention there's the person cost in terms of the amount of people they need to employ to try to do this manually in terms of checking all the documentation, all that kind of stuff. As it relates then to any kind of QA/QC and things like that. So first and foremost, our goal is to be able to facilitate the data flow through the supply chain, because that's the most difficult part, is getting the data in and then making sure that you can properly account for data as it flows through. We make sure in that process that data is not duplicated, double counted. One of the biggest risks is if everything's spreadsheet based, then someone can send the same spreadsheet to two different counterparties. So we eliminate that double counting. And then we do checks on the data. So one of the biggest things we do is address validation, which might seem like a nominal task, but it's actually really difficult to do at a global scale to make sure that addresses that are provided for where feedstock came from are actually valid addresses or geolocations. And then on top of that, we'll look at volumes to make sure they're consistent with averages, anomaly detection, things like that. And as we get more and more data, we can become more robust in terms of the type of QA/QC we can employ.
What is your model, subscription or per unit? And then have you guys considered for the data integrity like a blockchain, like some of the other auditing? And have you survived an audit?
We've survived a ton of audits. We have to deal with auditors all the time. And to your question about blockchain, so when we first got started, we thought about doing a blockchain application. The problem is if you really do blockchain, then you're decentralizing all the validation across the nodes. And this is the easiest way to put it. I'm trying to get people to convert from paper to a mobile app, having to explain to them that they're going to somehow have their stuff tokenized in real time and then validated. And if it fails that validation, they have to do something. It's an impossible task. So really we had to decide between, do we care about blockchain or do we care about getting data into the system? We chose data because fundamentally blockchain really is just the validation that the data came in and that it didn't change through the supply chain. We can do that anyway. And we can do that on a centralized level, and we can validate it externally using Amazon Web Services and other technologies. So blockchain, while it's a great buzzword, and if we were going for venture capital, I would totally think about it differently. Practically, it doesn't add a ton of value for what we're trying to do. Our model is usage-based, so we charge on a per pound, per ton basis. That's intentional for a couple of reasons. One is we want it to be low cost for folks to start using us and trial and figure out whether or not we work. We also want to prove our value to them within their marketplace. And so if we can improve their incremental economics because their product becomes traceable, we get a share of that, and it's a very minimal share, but we're able over time to show them the value, and then they're willing to pay for it.
Very, very good. Thank you for. And Eloy, I'm very familiar with NREL. How do you fit with the NREL ecosphere of research and support on energy?
Yeah, so I mean, we work a lot with NREL, but NREL has a lot of limitations, and that's usually when they come to us or we partner with them. And typically those limitations have to do with scale up. So our scale tends to be, we have large pilot plants. We have a universal air permit that allows us to quickly get pilot plants up and running, so we don't have to apply for any permits. There's potentially some safety concerns they have that we help overcome. So I guess we have a lot more flexibility on the size and exactly what kind of work we can do. We do things that probably, I can't even talk about. But yeah, so there's that's probably the main difference. They focus much more on the fundamental, which we're much more on the applied. Even though some of the slides I presented were kind of fundamental research, but our focus is on the scale-up side of things. And we probably max out around 400, 500 pounds per hour capacity for a pilot plant like that. Okay. So, yeah.
Very good. That's National Research Energy Laboratory. Sorry, I hate to throw acronyms out. So basically, you get the people with great ideas and a lot of cash.
Yeah, they're that next step. Yeah, they're in the multi-million-dollar development.
And Joelle, does your facility take the disaster and the fire waste as well, or are some of the disaster organizations in different states, they get waivers to basically landfill everything? How does Hawaii, or how do you guys get those large amounts, and how do you process those?
Okay, so our facility is not yet in the ground.
Oh, okay.
But to answer your general question, yes, of course, construction, demolition debris, and hurricane debris are not that different. Debris left over from a fire is different, of course. The energy content's pretty much been taken out of it. And we can provide sort of some advice on, ash handling and management. But unfortunately, thanks to the Lahaina fire a year ago, a lot of people in Hawaii's emergency management know a whole lot more about ash management now. And there's been lots of other ripple effects from that particular disaster.
Do you also plan to take electronic waste and separate as well for value? I mean, that's e-waste is the big export issue. Is your facility planning to accept any of that?
There's an ecosystem of recyclers in the city and county of Honolulu and in the state of Hawaii. We partner with ones that have existing capabilities. There's really not much as far as end-use markets in the middle of the Pacific Ocean. And so the electronics waste that is collected is usually actually shipped to California, and their recyclers here handle it.
And the general panel question, Jeff Bezos is the great master of Amazon and also the single largest buyer of cardboard. And so the question on the panel is, what do you have to deal with the mix and the shift towards more cardboard waste in the entire waste stream? So for your equipment, are you facing more challenges with the cardboard load?
I think in general the issue with the cardboard is that it is getting smaller and smaller, and the traditional technology to screen it out doesn't really work, so it requires more optical sortation to get the cardboard out of the mixed paper.
I'd say from our perspective, one thing that's been interesting is the cardboard actually has a fairly high amount of sulfur in it. So in a thermochemical, I don't know, maybe it's because of the antimicrobial coatings, but it actually ends up being higher sulfur than the wood. In our particular, the way we set up our system is construction, demolition, debris. Everything that's burnable, except PVC, goes into the gasifier. So cardboard is actually a great feedstock, and we just assume that there's going to be a certain amount of it in the feed, and so that we need to have the sulfur removal processes downstream.
Eloy, are you seeing any new technologies that can attack cardboard quickly?
Yeah, well, for our purposes, we don't care. We like cardboard. But what we're looking at is, if anyone wants to start a new company with us, is ways of integrating CO2 absorbent material into cardboard. This way, all those boxes are sitting out on your porch are actually absorbing CO2, and everybody will be happy, and Jeff Bezos would get the credit. But yeah, that's the kind of application we're looking at, like trying to find ways of adding things to cardboard to help them be more environmentally friendly in that sense.
That's really a good idea. I didn't think of that. And Dana, you could have a whole new industry base if you think about it.
Well, I'll pivot off your question slightly and take the Amazon side of it. So Amazon's one of the largest consumers of renewable fuels in the market, and they are a really interesting use case for the demand profile from more of a voluntary perspective, because they have their own additional requirements that they add. So when they're delivering these packages and they want to consume renewable fuel, they'll say, okay, I don't want it to come from this type of feedstock. I don't want it to come from this country of origin, things like that. So you layer that onto regulated markets, and now feedstocks that are leading into fuels that are getting consumed by these corporates have to meet all these additional requirements. And so all the more reason why you as you think about your feedstock and how you're going to document where it came from and the data behind it, it adds value downstream, because then these corporates, when they're looking to buy, can be more deterministic, and ultimately that will lead to commercial dynamics, because the more narrow they are in their purchasing decisions, the more they have to pay for that product.
Yeah. Yes, sir.
This is for Hartmut. Hartmut, you sort of opened my eyes to this chain of custody of feedstocks coming in. We've been using a lot of post-consumer plastics, all 7 types. We've never concerned ourselves with this chain of custody. Are we liable to be in trouble for that? Is that something we need to start doing? And what do you find is the percentage of your expense dealing with that chain of custody?
I'm not sure how to answer that question for you, because we're not tracing any material per se.
Excuse me.
Dana, you
Give the
meant Dana.
microphone to the man next to you. I'm sorry.
And that'll be our last question, and then we'll break to support the sponsors, which I think you're one of, and Dana is too.
Yeah, so I'll answer it this way. It's hard to say exactly what your liability is. I do know that
There are collectors out there, and basically for 7 cents a pound, which is the cost of collection, we're not paying for the plastics.
Yeah, and ultimately, there's the regulatory side of it, but if you're not the liable party from the regulatory side, then whoever is going to push that up to you, and then you're going to have to push that upstream contractually. And so what I've seen time and time again across all the different verticals within these markets is that's kind of how it goes. Whoever the regulated party is,
right.
Or within the voluntary market, whoever's selling the ultimate credit for that value, once they start to see pressure from auditors, that's when they change their contractual language. You'll then start to see those changes, and then you'll want to employ that upstream. So it's a long way of saying that, are you liable? You may or may not be liable today, but if you don't have a good accounting of that chain of custody, it's only a matter of time before someone's going to come ask you.
You're meaning liability to get paid or liability for the material?
Well, the liability that he insinuated because of all the regulation and
No, it's mostly about the feedstock traceability. To get paid, only certain feedstocks are eligible, and there's no downstream usually liability like disposal and things like that. He's collecting data so someone gets paid that the source of the material was correct and wasn't made up on a spreadsheet somewhere. That's what his traceability is focused on. But that is our last question, or we have one more, sorry.
For Eloy, one quick
Oh,
one.
sorry.
It's
Go ahead.
just a yes or no answer. At your facility, can you laboratory scale a pilot plant and get to an energy mass balance and subsequent scalability?
Yes, that's exactly
Great.
what we do.
I'll see you in San Antonio.
All right, we have one more. We have one more right there.
So related to the last question, in order to do advanced recycling, table stakes, absolutely gating is to have ISCC plus certification. So tracking, all of that is critical. So there are means for that. You mentioned that, and that's great. But if you could apply what you do to that world, that's key. And yeah, back to the other question is, yeah, it's needed. So like for number 4s, a lot of the chemical recyclers like ourselves, Brian from Resynergy, yeah, that's gold, and that certification is gold. So your application is great.
Yeah, and I talk to the ISCC technical team once a month. We're becoming integrated with their hub. We have a mass balancer to allow for being able to track product in, product out, and do it on a quarterly basis in alignment with their standards. So we're fully aligned with their certification.
Okay, this panel is finished on the 4, and we'd like to thank everyone.
Thank you,
Quick
panel.
round. Gene?
Let's do this real quick. All right, so we're ending a little bit early, so let's reconvene back here in 30 minutes, and that way everybody can get on the road a little bit earlier. Julie's here. Tim. Where's Tim Wachomp in here? Okay, fantastic, Tim. I just need to get a hold of Joe, make sure he's okay. Let's meet back in here in 30 minutes, and we'll wrap up the last section.
Again, thanks
Thank
to
you.
all the panelists. Thank you. Thank you.